Assalamu alaikum. We are Group 4. Myself, SM Rakib Hassan, ID 2224138. My teammates are Akar Dhakal, ID 20201203, and Maisha Noor, ID 20301379. We are here to present about Chapter 7, Neural Networks and Neural Language Models from the book Speech and Language Processing by Daniel Jurafsky. So let's start from units. So the building block of a neural network is a single computational unit. A unit takes a set of real valued numbers as input, performs some operations on them, and produces an output at the back. At the back, a neural network is taking a weighted sum of its input with an additional term. This term is called the bias term. Here's the formula of the weighted sum Z. Sometimes it's often more convenient to express the weighted sum using vector notations. Now, if you talk about Z in terms of a weight vector W, a scalar bias B, and an input vector X, and hence the formula for Z will be Z equals to Wx plus B. There are different activation functions for units. They are sigmoid, tanh, and ReLU. The sigmoid function is also called a squashing function, as its domain is the set of all real numbers and its range is 0 to 1. In practice, the sigmoid is not commonly used as an activation function. A function, hyperbolic tangent or tanh, that is very similar but almost always better is this one. Tanh is the variant of the sigmoid function that ranges from -1 to +1. The simplest function and maybe the most commonly used is the rectified linear unit, also called the ReLU function. It provides non-linearity and removes vanishing gradient problem. Now let's talk about the XOR problem. In case of a single perceptron, it cannot solve linearly non-separable functions, such as an XOR problem. In XOR problem, the truth table states that the output will be 1 if both inputs are different. So it clearly cannot be linearly separable, as output 1 is produced when the inputs are either 0, 1 or 1, 0. There is no decision boundary that can separate XOR function. The solution here is to use a neural network, more specifically multilayer perceptron. A multilayer perceptron can solve the linearly unseparable XOR problem. Next, we have the feed-forward neural network. Feed-forward neural network is a multilayer network in which the units are connected with no cycles. The outputs from units in each layer are passed to units in the next higher layer, and no outputs are passed back. There are a higher number of hidden layers and higher layers consisting of weighted sum of nonlinearity. On the other hand, the fully connected layers provide flexibility. Now let's talk about some important notations of feed-forward neural network. Here W means the weight matrix for first hidden layer and B means the bias vector. And B means the bias vector for the first hidden layer indicates the output layer and G is the activation function. Now here one of the reasons we use nonlinear activation functions for each layer in a neural network is that if we did not, the resulting network is exactly equivalent to a single layer network. So that will be all from my side. Thank you. Now my next teammate will discuss about the concept map.
Assalamu alaikum. I am Maisha Noor. My ID is 20301379. Um, I will talk about the applications of feed-forward networks, and I will start with the classification task. Previously, we learned features where we multiply it by weight functions, then add the bias term, then we pass it through the activation function. After that, we multiply it with the weight matrix U and pass it through the softmax. And that's how we receive Y, which is the probability distribution. Now, by expressing words as the embeddings, we make use of deep learning's capacity to learn features from the given data. There are various ways to represent any input for classification, and one simple baseline is pooling, which is used to apply some sort of pooling function to the embeddings of all the works in the input. For example, text is taken with n input words or tokens, which of word W1 to Wn, which we can turn into embeddings to E of W1, E of W2 into a single embedding, also by just summing the embeddings or by taking their mean. Now we will look at the second application of feed-forward networks, which is neural language modeling. Uh, Now, neural language modeling can handle more histories than n-gram, and this is its advantage over n-gram models. But on the other hand, it is complex, slower, and less interpretable than n-gram models. Now, our feed forward takes as input at time t and a representation of some numbers of previous words and provides output of a possible probability distribution over next possible words. Neural language models represent words in this prior context by their embeddings rather than just by their word identity as used in the n-gram language models. So, using these embeddings, this allows neural network models to generalize better to unseen data. Now we'll talk about forward interference, which is the task given an input of running a forward pass on the neural network to produce a probability distribution over possible outputs. In this case, next words, we first represent each of the n previous words as a one hot vector of length one hot vector v with one dimension for each word in the vocabulary. A one hot vector is a vector that has one element equal to one in the dimension corresponding to the word's index in the vocabulary, while all other elements are set to zero. It has a moving window that can see n words into the past. Now, we will look at a sample algorithm. At first, we need to select three embeddings from the matrix E, after which we need to multiply it with the weight matrix W, and then we need to multiply it with U, and finally apply softmax over it to receive the final probability distribution. Now, my groupmate Akar will talk more about it.
Assalamu alaikum. My name is Akar Dakal, student ID 2020-1203. So my teammates have already discussed some subtopics from the main topic. Now I'm going to discuss the last two remaining subtopics, which are training neural networks and training the neural language models. At first, I'm going to talk about how we can train neural networks. Neural network training is the process of teaching a neural network to perform a task. Neural networks learn by initially processing several large sets of labeled or unlabeled data. By using these examples, they can process unknown inputs more accurately. First of all, we will need a loss function. A loss function measures how well a given machine learning model fits the specific data set. It boils down all the different underestimations and overestimations of the model to a single number known as the prediction error. It's common to use the loss function used for logistic regression, which is known as the cross entropy loss. Secondly, to find the parameter that minimizes this loss function, we will use the gradient descent optimization algorithm. And finally, the gradient descent requires knowing the gradient of the loss function, the vector that contains the partial derivative of the loss function with respect to each of the parameters. To compute this gradient, there is an algorithm called error backpropagation or backprop. While backprop was invented specifically for neural networks, it turns out to be the same as more general procedure called backward differentiation, which depends on the notion of computation graphs. Talking about a computation graph is a representation of the process of computing a mathematical expression in which the computation is broken down into separate operations, each of which is modeled as a node in a graph. In the forward pass of a computation graph, we apply each operations from left to right, passing the outputs of each computation as the input to the next node. The importance of computation graph comes from backward pass, which is used to compute the derivatives that we will need for the weight of data. For backward pass, loss is always computed. Updating learning rate is another important factor in backward propagation. So there are some other factors regarding how we can train neural networks. These factors are known as dropout, hyperparameter tuning, regularization, or parameter reduction, and etc. So these are done to improve the accuracy and stability of the neural networks. There are several ways to find out sweet spot for different parameters values, and usually people follow either straightforward trial and error method or the parameter tuning method to get the best value. So this is all for training neural networks. Now I'm going to talk about how you can train neural language models. We have seen how to train a generic neural network. Let's talk about architecture for training a neural language and model setting, the parameters. Theta equals to EWB. Here E is the embedding matrix, B is the bias, and W and EO are two weight matrices. For some tasks, it's okay to freeze the embedding layer E with the initial word to vec values. Freezing means the word to vec values or some other retraining algorithm to compute the initial embedding matrix E and then hold it constant while we only modify W and B. For example, we don't update E during language model training. Training neural language model is done using gradient descent. This gradient can be computed in any standard neural network framework, which will then backpropagate through theta equals to EWUB. Training the parameters to minimize loss will result both in an algorithm for language modeling as a word predictor and also as a new set of embedding E that can be used as word representation for other tasks. So this is how we can train neural language model, and that is the end of my presentation. Thank you.